Dear students, today I am going to discuss about the fundamental property equations. So this topic belongs to CO3 biochemical thermodynamics. So let's see the aim of this session. So this session deals about the basic concepts of the fundamental property equations. So the main objectives of this session are describe the significance of fundamental property equations and summarize the four fundamental property equations. So ultimately students can learn the significance and the fundamental property, the significance of the fundamental property equations in biochemical thermodynamics. So let's start the introduction. In thermodynamics, many variables are there, thermodynamic variables. So some thermodynamic variables can be measured directly. So many thermodynamic properties cannot be measured directly. So it is necessary to develop some relationship between these measurable quantities to the unmeasurable quantities, so that the properties that cannot be measured directly can be estimated through measurable quantities. So for example, some measurable quantities in biochemical thermodynamics are temperature, pressure, volume and entropy. Unmeasurable quantities are, most of the unmeasurable quantities are energy properties. For example, internal energy, enthalpy, Helmholtz free energy and Gibbs free energy. These energy properties cannot be measured directly from the thermodynamic system. So that's why these four properties, these four energy properties called as unmeasurable quantities. So if we develop the relationship between these two groups, that means measurable quantities and unmeasurable quantities, in the form of differential equations called as fundamental property relations or fundamental property equations. So the differential forms of these four properties relating to the natural variables or thermodynamic properties. So these equations are developed under a constant mass and under constant composition of a defined thermodynamic system. So before going to first fundamental property equation, let's see the first law of thermodynamics for a non-flow process. In the previous classes, we derived the mathematical statements of first law of thermodynamics for a flow process as well as for a non-flow process. Now let's see the mathematical statement of the first law of thermodynamics for a flow process, for non-flow process. So the equation is represented as du is equal dq minus dw. So in the previous was we discussed the delta u is equal to q minus w. This is the simple mathematical statement of the first law of thermodynamics. This was discussed in the previous classes. Delta u represents the change in the internal energy, and q is the amount of heat energy supplied to the system, and w is the amount of work done by the system. So this what discussed in the previous session. Okay, so by differential form of this mathematical statement of the first law of thermodynamics, we can get this equation du is equal to dq minus dw. Okay, so from the second law of thermodynamics, dq is equal to T into ds. This T into ds means ds is the change in the entropy, T is the absolute temperature. from the second law of thermodynamics. In the same way, the change in the work done by the system or amount of work done on the system can be measured by the product of pressure and change in the volume. How to estimate the work done by the system? How much pressure is applied, how much volume is changed in that system. The product of pressure and change in the volume gives the amount of work done on the system or by the system. So then by substituting dq is equal to tds and dw is equal to pdv, then the equation 1 becomes du is equal to tds minus pdv. So tds means dq, pdv means dw. Just dq and dw are replaced by tds and pdv. So this is the internal energy. The change in the internal energy in the form of differential form is equal to tds minus pdv. So before going to first fundamental property equations, once again recap the session. Energy properties such as internal energy, enthalpy energy, Helmholtz free energy or work function, Gibbs free energy cannot be determined directly from the thermodynamic system, but we can measure the temperature, pressure, volume and entropy of the system. That's why if we develop the relationship between these natural variables such as temperature, pressure, volume and entropy to the energy properties such as internal energy, enthalpy energy, Gibbs free energy and Helmholtz free energy, then we can estimate the unmeasurable quantities like energy forms in the form of natural variables. Let's check the first fundamental property relation. Okay, the first fundamental property relation is called internal energy equation. So this is let's start with first law of thermodynamics, delta equal to q minus w. Okay, so this is what derived in the previous session. This is the mathematical statement of the first law of thermodynamics. This is called first law of thermodynamics. By applying the differential form, to this equation, we can get du is equal to dq minus dw. Okay, so dq and dw are replaced by tds and pdv. This is what we discussed in the previous slide. So dq can be replaced by tds and dw can be replaced by pdv. So the final internal energy equation can be written as du is equal to tds minus pdv. That means the change in the internal energy is a function of volume and entropy. These are the canonical function of volume and entropy. That means the internal energy highly dependent upon the volume and entropy of the system. If we know the temperature, entropy, pressure, volume, then we can able to determine the change in the internal energy of the system. So du is the change in the internal energy of the system, that is unmeasurable quantity, can be estimated through by temperature, pressure, entropy and volume. In the same way, let's see the second fundamental property equation. So what is the second fundamental property equation? Enthalpy. So let's start with enthalpy equation. So what we discussed in the previous classes, the definition of enthalpy is equal to internal energy, sum of internal energy and amount of work done on the system or by the system, that is product of P and V. Simply the enthalpy means it is the total heat content of the thermodynamic system. By mathematically H is equal to internal energy plus PV is equal to external work done by the system or external work done on the system. So the sum of internal energy and external energy gives the total heat content of the system, that is called enthalpy. So let's apply the differential form to this enthalpy equation. So we can get dH is equal to du plus PdV VdP. If you know mathematically, d of uv is equal to u dv plus v du. This is the simple mathematical differentiation form of duv. So similarly, therefore, dH is equal to du plus PdV plus VdP. So previous fundamental property equation 1 derived for internal energy. Du is equal to TdS minus PdV. Just substitute here, substitute this first fundamental property equation in the place of du. Then we can get the TdS plus VdP, because minus PdV, this minus PdV and plus PdV, this both will be cancelled. We can get the TdS plus VdP. So this is the second fundamental property relation between enthalpy to the temperature, entropy, volume and pressure. So canonical functions of the enthalpy related to pressure and entropy. So by knowing pressure and entropy at a constant temperature and constant volume, we can estimate the enthalpy of the system. Similarly, let's go for the third fundamental property relation. So this third fundamental property relation, also called as work function or Helmholtz free energy, is also called as a work function. So the mathematical statement of the work function or Helmholtz free energy is written as A is equal to U minus Ts. What is U here? U is internal energy. U is called internal energy of the thermodynamic system. Minus Ts represents the, it is free of entropy. Whenever you can get minus Ts means free of entropy. So if you subtract the entropy energy, that means Ts, from internal energy, you can get the amount of useful work of the system, that is called Helmholtz free energy or work function. So for example, whenever you can get free energy, gives free energy, Helmholtz free energy. Free energy means free of entropy. That means let's understand this free energy concept in a simple example. If you buy 12 mangoes, 1 dozen mangoes from a market, once we come to our home, 2 mangoes are identified in a damaged mode or decomposed. Then what are the total useful mangoes? 12 minus 2. 12 minus 2, that gives the 10. If you subtract that damaged 2 mangoes from 1 dozen mango, we can get the useful mangoes or eatable mangoes 10. So in this way, here the total internal energy U minus free entropy energy, free from entropy energy. If you subtract the entropy energy from the internal energy, you can get the useful work, that is called work function. Okay. Let's apply the differential form of this equation. dA is equal to du minus TdS minus SDT. As we know, simple mathematical expression, differentiation of uv is equal to u into dv plus v into du. Apply the same simple mathematical differentiation form to here. d of Ts is equal to TdS and SDT. There is a minus sign here. d of Ts is equal to TdS plus SDT. Okay, so there is a minus sign, that's why minus TdS minus SDT will come here. So in the previous the first fundamental property equation du is equal to TdS minus PdV, substitute this expression here, we may get a final fundamental property equation between Helmholtz free energy and in terms of temperature, pressure, volume and entropy. So the Helmholtz free energy or work function is highly depends upon the canonical variables of temperature and volume. That means if we know the temperature and volume at a constant entropy and pressure, we can estimate the unmeasurable quantities such as work function. Okay, so similarly in the same way, let's go for the fourth fundamental property equation. So the fourth fundamental property equation is called Gibbs free energy. So let's see the mathematical statement of the Gibbs free energy. G is equal to H minus Ts. What is H? Enthalpy. What is minus Ts? This is called free entropy energy. That means if you subtract the entropy energy from the total enthalpy, we can get Gibbs free energy. Minus Ts means free from entropy. Okay, so H represents the total heat content of the system. By subtracting the free entropy energy, then we can get the useful amount of energy, that is called Gibbs free energy. Okay, so before going to this fundamental property equation, let's talk about the Gibbs free energy. It is the energy of a molecule or reactants at which decides the or characterize the nature of the equation. If you get the change in delta change in Gibbs free energy, by knowing change in Gibbs free energy, whether it is delta G greater than 0 or less than 0 equal to 0, we can characterize that equation as a endergonic reaction or exergonic reactions. Okay, so it is the standard energy of the molecule, or it is an inherent or inbuilt energy of each and every molecule in the universe. So let's apply the differential form to this mathematical statement of Gibbs free energy. We can get the dG is equal to dH minus TdS minus SDT. Similarly, what we discussed in the previous example, applying the differentiation form of Ts, d of Ts is equal to TdS plus SDT. So by substituting previous second fundamental property equation in the place of dH, you substitute here in the place of dH, then TdS plus VdP plus TdS and minus TdS, it will be cancelled. We can get VdP minus SDT. So the final fundamental property equation is minus SDT. This both will be cancelled. It's round one, both will be cancelled. It will be, you can get the final fundamental property equation of Gibbs free energy. dG is equal to minus SDT plus VdP. That means the Gibbs free energy is the function of the temperature and pressure. If you know the temperature and pressure at a constant volume and entropy, we can estimate the Gibbs free energy of a thermodynamic system. So these are the four fundamental property equations. So let's see the summary of this session. In thermodynamics, there are four fundamental property equations or expressions or relations. The first fundamental property is related to internal energy, that is mathematically defined as delta U is equal to Q minus W. The fundamental property in terms of temperature, pressure, volume and entropy is equal to du is equal to TdS minus PdV. This is called the first fundamental property equation. Similarly, second fundamental property equation related to enthalpy and natural variables. H is equal to U plus PV, therefore dH is equal to TdS plus VdP. This is called second fundamental property equation. Similarly, third fundamental property equation, which is related to Helmholtz free energy or work function, that is denoted by A is equal to U minus Ts. Minus Ts indicates the free of entropy, or by subtracting entropy energy from the internal energy is called useful work done by the system, that is called Helmholtz free energy or work function. Mathematically, it can be deduced as dA is equal to minus S dt minus P dV. This is called third fundamental property equation. So last one, the fourth fundamental property equation is related to Gibbs free energy. G is equal to H minus Ts. So it is derived in terms of temperature, pressure, volume and entropy, represented as dG is equal to minus S dt plus VdP. These are the four fundamental property equations. So all these fundamental property equations express the energy properties in terms of four reference properties such as pressure, volume, temperature and entropy. So all these four energy properties generally cannot be measured directly, but can be estimated through reference properties or primary properties or natural variables such as pressure, temperature, volume and entropy. Okay. So these are the self-assessment questions based on the properties of the thermodynamics. In thermodynamics, there are number of properties are there. Those properties are classified into three groups: primary properties or reference properties, secondary properties or energy properties. Third one is tertiary properties or derived properties. Okay, so primary properties or reference properties called as these are the exactly measured directly. That means we can measure it directly. Those properties are called reference properties or primary properties, such as temperature, pressure. These are called temperature, pressure, volume and entropy. These properties can be measured directly. And energy properties means these properties cannot be measured directly, but we can estimate these energy properties through reference properties. What are the energy properties here? Internal energy, enthalpy, Helmholtz free energy and Gibbs free energy. These are the energy properties. Okay. So these are the reference books for the biochemical thermodynamics. Thank you for watching this video.